kind of a piggyback right off the video. So in the video, you guys looked at 3 sums, am I right? 3 types of sums? Can you guys name them?
Left sum, right sum, midpoint sum.
Yep, left, midpoint, and right. That is all correct. And so the point here is about approximation. Finding area under a curve. We'll talk about this a little bit more later, but the concept of trying to figure out how much area is like under a parabola or how much area is under like a sine or a cosine curve, something like that, is very, very old. It's actually thousands of years old, whereas differential calculus is only a couple of hundred years old. And so you can imagine mathematicians, geometry people over the years from all across the world thought we know how to find the area of a square, area of a rectangle, a triangle, stuff like that, but how on earth do we find the area under a curve? And so you start off with approximation. You think, well, if I take a known figure, like a rectangle, and I use that to approximate the area under the curve, this will give me a starting place, right? So that's kind of where we start. So in the video, you guys saw a lot of pictures of these sorts of examples. But in number 3, this is where it's a little bit different. This will be often the format that you'll see a question like this. You'll be given data in a table or tabular data to get you started here. So notice the description here says a polynomial function f of x is differentiable and continuous on 0, 8. Values of f are given below, and it just gives you this table, kind of all over the place. And then part A says use a left sum to approximate the area of the curve, and B is use a right sum. So what I thought I'd do is kind of work on A with you guys and show you a couple of different angles you could take with it, and then I'll have you guys try B on your own, because B, although different, is similar enough. That make sense? All right, so here is one way of thinking about this. If you want, you could take the data in the table and essentially create a picture, create a graph. So this would be one suggestion for you. So I'll do that. So if I've got a y-axis and an x-axis, then my graph, let's see here, we go as high as 242. It's going to get way up there. So I'm going to go like that. Here is a potential graph. So 0, 18 would be right about there. 132 would be, say, right about there. 372 would be higher than that. 7,200 would be up there somewhere. And then 8,242 would be just a little higher than that. So, I don't know, does it sort of look like part of an upside-down parabola? Or maybe part of a sine curve or something? It obviously has a little bit of curve to it. And so it is supposed to be a differentiable and continuous polynomial function. And so we could connect these dots with a nice smooth curve like so. And this is a representation. And we don't know that that's exactly what it looks like. Because you guys know, of course, that between any 2 points you could have a bunch of this stuff, right? You could. We don't know. But you could have that. So I'm going to get rid of that because we don't know about it. But we are expected to find a left sum. So I'm going to draw in a left sum. This will kind of look like what you had on your video. So a left sum is going to use the left side of the interval to determine the height of the rectangle. So my first left sum rectangle would be right about there. And then my next one would be there. Third one would be here. Fourth one would be, pardon the waviness to my rectangles. I hope you get the point still. Anyway, does that make sense from the perspective of a left sum? Okay, so let's think about how this would work. This is 1 right here. So as far as finding the area, so I'll just go one by one here. So my first rectangle is right here. What are the dimensions on that first rectangle that I just kind of filled in? 18 by 1. So yep, I'm going to say, I'll put LS for left sum equals, start off with 1 times 18. What are the dimensions of the second rectangle that I'm highlighting in right there? 2 by what?
2 by 32.
It's 2 by 32. And here's how you know that. If you look back at the table, let's see here. The second rectangle is based on the height of the curve at 1, right? and the height of the curve at 1 is 32, and so 2 times 32. All right, is this going okay? Third rectangle is right there. What are the dimensions on that guy? 4 by 72, yep. So area, of course, is base times height, 4 times 72. And then finally, the last one is 1 by 200. So 1 times 200. So a couple thoughts on this. I am going to show you an alternative thought on this that you could do without the help of a picture. But one thing I think it's really important for you all to realize, if I ask you, or if the AP test asks you to use a left sum to do anything, I need to see evidence of a left sum. So I want to give you some examples here. Like, we all know that 1 times 18 is 18, obviously, right? We all know that 1 times 200 is 200, but I still want to see that base times height concept going on in there. Does that make sense? So please don't shortcut that. Now, if you can do all this math in your head real quick, or you have a calculator, you can do it all real quick, that's totally fine, right? No big deal. But I do want to see evidence that you used a left sum. So let me give you an example of something that might look real good, but would not show evidence of a left sum. So check this out. What if I wrote something different? What if I wrote left sum equals 18 plus 64 plus 288 plus 200? Those are all right numbers, aren't they? Is there any evidence that you actually did a left rectangular sum? None. Okay, so while you might get a correct answer on this one, if you added all those things up correctly, you would not get credit for the showed evidence of a left sum point. Okay, so I just want to be super duper clear with that. Does that make sense? Okay.
What if you do a graph and then with that?
And I got to see it in the numbers, right? Because graphs are notoriously a tad unreliable. I will say, though, sometimes AP readers do take it, but it's inconsistent. So as a reader for 5 years, I've done a question like this maybe like 3 or 4 times. And I know for sure 1 year, they just said, if you see a graph, ignore it completely. Just look at what the numbers and the equations and that sort of thing, the expressions are saying. Other years, they're like, okay, so if they got a graph and it's really well labeled and they have this and this and this and this, it was like very much prescribed, then we were able to accept that. But they've always taken an expression like what I've got up there at the upper right. Okay, so you add all that up. Sorry, Catherine, we'll add it all up after your question. Go ahead.
I'm sorry. I was wondering why we didn't create another rectangle for 8. Is it because it's 0 to 8 and finishes there?
Yeah, so it just says area under the curve. We don't really know what happens to the curve past 8,
Okay.
right? So you could try to create a rectangle over there, like that, but then like how far would it go?
Right.
We don't know. So once we get to 8, with our rectangles, we just stop. And you said it well, just because of the interval that we're given. So we add all that up, 82, 370, 570. Yeah, okay, 570. So if you were doing a question like this on, say, a free response, I would want to see 2 things. I'd want to see evidence of a left sum, and then, of course, a correct answer to go along with that. So there you go. Could I show you an alternative about what you could do here? Like a different way of thinking about it. A picture is a good way, and I've got no problem with that at all. I am going to erase all of this and show you an alternative way. If you're going to do a left sum, here's what you could do. You can just work with the table, and you can say that the x's will be giving you your base lengths, and the correct y will be giving you your height. So what I would do is I'd say my first interval is from 0 to 1, and so my base length is 1, and I'm going to use the left height. Does that make sense? So you don't have to draw a picture here. You could just say 1 times 18 based on that kind of thinking. And then you could say the next interval goes from 1 to 3, and so the base length there is 2, and I'm going to use the left height. So 2 times 32. And then you could say plus, that next one goes from 3 to 7, so that's a base length of 4, and I'll use again the left height, 72, and then the last one, 7 to 8, is a base of 1, so it'd be plus 1, and I'll use the left height, so times 200. Okay, so you can definitely do it that way if you want. No way am I ever going to require you to draw a graph. If you can see it in the table, and I do hope that eventually you'll get to that place where you can just say, hey, table, left sum, done. And then, of course, you just add them all up, and you get 570, and you'd be done. Okay, so I showed you two different ways of thinking about it, one with a picture, one just by kind of reasoning within the table. What do you think? Do you have any questions? Okay, well, let's, why don't you try your hand to write some? Let's use the same data, see if you guys can do part B on your own. I'll clear all this stuff off, and you guys can try it, and we'll check your answer in a couple. Let's try this out.
I'm trying to do a surprise interruption. Or what was it called again?
Disruption.
Or intriguing disruption.
Oh, bizarre.
Bizarre.
Yeah, I don't want that.
All right.
That's not good. All right, so here we go. Left sum equals. So guys, I'll take the reverse approach on this one. Guys, listen up, please. I'll draw a picture second if needed, but at the start here, I'm going to simply just write out the right sum formula. So this should be, how about RS for right sum? So right sum, what I would do is I would look at this first interval, and again, notice the base length is 1, but this time I'm going to use the right height, the one on the right every time, the right side of the interval. So it'd be 1 times 32. Plus the next interval is from 1 to 3, so once again that has a base length of 2. I'm just looking at the difference between those, but I will be using the right side height there, so this time it's going to be 72. Plus the next one goes from 3 to 7, so that's 4 times, I'll use the right side of 200. And then lastly, we go with 7 to 8, base length of 1, height of 242, because I'm using, again, the right side of the interval to determine my height. So I am totally okay if you just write it out like that, and you don't even have to make the markings in the table. I don't really care if that helps you, do it. If a picture helps you, do it. But we want to get to that. That right there is evidence that you've done a right sum, and we're in a good place. Question?
If it was the midpoint sum, would you just find the midpoint between like 18 and
We'll talk about that in a second. That's a good question. I was actually thinking about that. But we'll get to that. Okay, so then if we do attempt to actually sum all the data up, 76, 9, 76, 11, 76, 11, 78. Do you guys get 12, 18? 12, 18, okay. Okay. Does anybody want to see a picture drawn? Would that be helpful? Or are you okay? Where are we at? I'm reading confident faces. Am I right? Okay. Okay, that's excellent. So I do want to address Catherine's question here real quick. And her question was, what would we do if you were asked to do a midpoint sum with this? I don't think that this question, as it currently stands, is set up very well for a midpoint sum. Say, for instance, I had that in here. Let's say I had part C. I'd have to say something like using 2 subintervals, use a midpoint sum, ... Use a midpoint sum to find or to estimate the area under the curve, something like that, right? So it's not set up very well. I'd have to change some of the numbers to make it be set up for that. For instance, does anybody know, like this 1 right here, if I turn that 1 into a 2, really?
What would it be though?
Is 2 really the middle of 0 and 3?
Oh,
How about
like
1.5?
Like from 0 to what? What would you change 1 to?
So I would have to change this 1 into a 1.5. Now, isn't 1.5 really truly the midpoint between 0 and 3?
Yeah.
So I could use a midpoint sum there. But then the other one, 3, 7, 8, the 7 wouldn't work. What would the 7 have to become? 5.5, I think. Yeah, 5.5.
Oh, you dad.
So the difference is 5. You split it in half, 2.5 from either side. It gives you 5.5. Yeah, so if I set it up like that, it would make the numbers less nice, but you could actually do a midpoint sum there. So I'll show you a midpoint sum. Midpoint sum, what would be the base length? There's only 2 intervals, right? There's the one that goes from here to here, and the one that goes from here to here. So in that first interval, what is the full base length? 3. Yep, 0 to 3. But then of the 3 heights that I have a choice to use, the 18, the 32, or the 72, which one do I use?
32.
The 32, because it's the height that goes with the midpoint. So it'd be 3 times 32 plus, what is the base length on the other triangle? 5. From 3 to 8 is 5, I agree. And I've got, again, 3 choices, 72, 200, or 242 for my height. What should I use? 200, because doesn't that go with the midpoint? So you'd multiply those out and you'd get 1,096. So midpoint sum, only if I rewrote it like that, midpoint sum could be used here. Otherwise you can't. So Catherine's question kind of was, if you did a midpoint sum, would you have to go in the table and kind of interpolate, and try to take a guess, like, for instance, the midpoint here would be 0.5, right? 0 to 1 be 1, split in half, 0.5. So would we say, all right, so then the y value must be halfway between 18 and 32. That'd be what interpolation would be, right? And so you'd say this would be 25, I think. The answer to that is unequivocally no. So if you are given a table of data, the question is intended to be answered strictly from the data in the table. It's not up to us to say, oh, and then in the middle it would be this, maybe, or something like that. So if you find yourself doing something like that, you are automatically doing the wrong thing. You want to do something different. Reread the question, figure it out, hopefully, and you'll be okay. That make sense? Okay, fantastic. Are you explaining interpolation? Sort of, kind of. What I did up there, you should never be doing, not in this class anyway. So if you find yourself doing that, just stop and say, I should be doing something else. Never add to the table. Just take the table data as is. So, I don't want to break my own rule. There we go. Okay, do you guys have any other questions? Okay, awesome. Let's see here. Let's move forward. We're going to... Oh, that is not what I wanted to do at all. Before, I don't know. Do both of my pre-calc classes here, do you guys look at sigma?
Yeah, we did.
So what does sigma mean, like that big capital sigma? Yeah, it tells you you're going to add a bunch of stuff up, right? So it's a notation for that. So let me think about how I want to do this. So a couple things I want to maybe allay some fears, because I'm looking at some faces. I see some unasked questions. So some examples of some of the unasked questions I see out there are, do I have to memorize that table? No, you do not. In fact, we may or may not actually ever use that table. We might use it on one question just to kind of prove something to you guys, but you do not need to memorize that table at all. We might use it in class just to illustrate a point, but please spend no effort on memorizing that. We will be adding a bunch of stuff up to, overgeneralize things a little bit. Definitely be adding a bunch of things up, and that's why we use sigma here. What we're getting at is basically this. Do you guys remember way back we talked about the derivative, and we talked about what is the derivative, and we talked about how it's the instantaneous rate of change, it's the slope at a point, the slope of the tangent line, stuff like that? Because if somebody were to say, I would hope that if you had enough time to just think clearly, if somebody came up to you and said, hey, you're in calculus, that's awesome. What is the derivative? I've heard about this. Can you tell me what it is? Get some time to think about it. You could maybe explain a little bit about what it is, right? What we're about to look at here is, what is the integral? Like, where does it come from? How do we get from point A to point B? And then we'll start using it in a little bit of a different way than you have even up to this point. So, I mentioned this earlier, that the idea of trying to find the area under a curve is very, very old. The oldest evidence of some civilization doing this is actually in China, well before the time of Christ, actually. There's somehow evidence of, hey, we're trying to find the area under a curve using rectangles or triangles or trapezoids or some kind of a geometric shape to approximate the area of the curve. So it's a very, very old problem. And so we get to kind of stand on the shoulders of these mathematicians from the past and be like, hey, we know how to do this. Doesn't mean that it's easy, but I'm thankful that they were able to figure some of these things out for us. That we can just kind of retrace their steps a little bit. And so let's see here. I want to give you just some real basics, and then we'll dive in. We'll do a couple of examples. So I want you guys to look at this. I'll circle it for you. I want you guys to look at this right here. I want to kind of pick this apart a little bit. It kind of goes with the graph over there to the side. So you can see it's a curve. They don't really tell us what curve it is, but you can see it's kind of curvy. You don't see the pink area under there? So it's kind of like we're trying to find the area between the curve and the x-axis, that pinkish area. And what somebody's done right here is they have drawn a rectangle in there to kind of represent, hey, we're using a rectangle kind of like we just did, to approximate the area, that pink area under the curve. So let's go back over to the thing I put in the black box right there, and let's focus specifically on this and that. This groundwork I think will be really useful for you. So when you look back over here at this rectangle, the purple one in the picture, the base length, right? The area of a rectangle is base times height, isn't it? So if I were to maybe highlight that, the base length would be right there, wouldn't it? And notice down here they say, hey, look, if I take the right endpoint minus the left endpoint, I get delta x. And so perhaps, I hope that this makes sense to you, that full width or base length of the rectangle would be delta x. So base length is delta x. And then the height, right here, they're of course using a midpoint rectangle, it looks like. The height of that rectangle, isn't the height determined by the y value of the curve? That's what we've been working on the video and what we just did with our example with the table. So the height of the rectangle completely depends on the y value of the curve at that point. And so what that means then over here on that box on the left, that means that delta x is simply the base of a rectangle, and the f of c is the height of a rectangle. You see that? Height times base? Okay. So then let's look at the other symbols. This sigma, of course, means sum. So this means we are going to be summing up a bunch of rectangles. Now, exactly how many? Doesn't it say from I equals 1 to n? So we're going to be summing up n rectangles, and that's very flexible, right? We could say if we want to use 30 rectangles, then n would be 30. If I want to use 10 rectangles, then n would be 10, etc., right? So that sets us up to be able to make the number of rectangles be whatever we want them to be. But then you look at the very first part of the expression, and that limit does what? Makes the number of rectangles, since we're flexible on that, makes the number of rectangles head towards infinity. So let's think about what that does. If the number of rectangles within that little pink space is approaching infinity, like the number of them is approaching infinity, then how wide would they be getting?
Infinitely small.
Closer and closer to which number?
0.
0, right? Closer and closer to 0. So they'd be like 1/10 wide, then be like 1/1,000,000th, 1/1,000,000,000th, 1/1 whatevereth, right? And they would just be, the width of the rectangles would be just getting skinnier and skinnier and skinnier. But the heights would be remaining whatever the height needs to be, right? It's based on the curve. If you did that, then wouldn't it be fair to say that you'd be filling that pink area with just a bunch of vertical strips, just 1 point wide, giving you the actual area? There's a lot of mechanics behind this, but I want you to try to get the concept of what we're trying to do here. Does that make sense? If you ever get confused by this, go back to this, base times height. That's definitely oversimplifying it a little bit, but that's the underlying concept on all of this, base times height. Okay, so we're going to do a couple of examples. How many is kind of up to you. We'll just see how it goes. You good? Okay, you can stick around if you want. No, maybe? Okay, all right. All right, so flip over to that next page, and we'll do a couple of examples like these. Caleb has already cut his teeth a couple of times on these. He knows. Okay, so take a look here at number 4. Okay, so number 4 gives you this this term I don't know that you've seen. Maybe, I don't know if I mentioned this in the video or not. Did I mention Riemann?
Oh, yeah.
At the bottom. Did I say something about all these are Riemann sums? Okay. So Riemann sums are named after this this German guy from way back when, GFBW. He has 4 initials for his first name. Seriously, GFBW, I think they are, Riemann. He is in the math circles extremely famous. He still has a theorem that I think to this day has yet to be proven nor disproven. It's his prime number theorem, and it's pretty intense. I read a whole book on it, and having done like differential equations and real analysis, and the whole list goes on, I've taken all these classes in colleges, I would say that I'm up to the level where I like barely understand it. I would say. Thanks, Caleb. It's a pretty complicated book. It's a very complicated theorem, but it basically revolves around the idea of being able to predict accurately how many prime numbers are less than any one particular number. Right? So if I just said, all right, the number is 20, how many prime numbers are there between 0 and 20? You could count them up. You'd be like, all right, 2, 3, 5, ... and you'd count them up pretty easy. But what if I said how many prime numbers are less than 20 trillion? A little more complicated, right? Yeah, sounds about right. Yeah, at least bigger than 17, yes. But it would be far more difficult to make a prediction or have some sort of a process of trying to prove that. That's more or less an oversimplification of what his prime number theorem is all about. Anyways, that's not what we're going to talk about today, thankfully. We're going to be talking about how to use Riemann sums. But it's the same guy, is why I bring that up. All right, so here's how we do this. It might be helpful for you to sketch out a quick picture. If it's not, no big deal. I am going to sketch out a brief, rough picture. So x cubed looks about like this. That's one of my better cubics. I'm happy with that. And we are concerned about the interval from 2 to 5, so I will just kind of throw that in here. So 2 to 5, we'll say is right about there. So what we are supposed to do here is we're supposed to write a Riemann sum expression for the area under that curve, or between the red curve and the x-axis. So we're talking about this area right here, like so. So if I asked you to do this yesterday or this morning, you probably would have used a left sum, a right sum, or a midpoint sum, understandably, right? And that would be a way to approximate it, but it certainly would not be the exact area under the curve. So what I want to do is we're going to take this from most easy and we'll finish with most difficult, okay? So if you are ever asked to write a Riemann sum or match up a Riemann sum with something, the first thing you're going to write is this: the limit as n goes to infinity of sigma from I equals 1 to n. They all look like that. So that's the easiest part here, right? They're all going to have like a limit sigma component to it, right? They're all going to have that. So we start by writing that, and then you can take some different strategies here. The other thing that's almost as easy is the expression that goes in the sigma is always, like we did before, base times height, or height times base, depending on how, ordering doesn't matter. So if you wanted to write that in there, you could say base times height, and then just sort of develop it from there. But that's kind of an easy start. Say limit sigma of base times height. They will all start this way. Make sense? Yeah? Okay, cool. All right, so let's go back over to the picture. And I want to start by thinking about my base. So I think the easiest thing to write is the limit sigma, right? We start off with that. To me, that's the easiest part. It's obvious. And then base times height, similarly, just as obvious. I think the next easiest thing is the base. Okay, so here's how we think about the base. I want you guys to kind of help me think this through. If I were to draw in a rectangle, hope this will be pretty visible for you. I don't like that color. If I were to draw in a rectangle like this, it's better. And maybe I could do another one over here, whatever. Fill this in a little bit. There'd be a bunch of them. Potentially, right now it looks like I could maybe fit like 5 in there if I kept doing what I was doing. But keep in mind, we're doing sigma from I equals 1 to n. So I want to be extremely flexible on the number of rectangles I can use, because I know in the end I'm going to make the number of rectangles approach infinity, right? So I want flexibility. So let's think this through. If I have this full interval width from 2 to 5, and I plan on filling it with n rectangles, right? That undetermined number of rectangles, we're going to give it a variable name like n. So I'm going to fill the whole thing up with n rectangles. How wide would each rectangle have to be? Well, you guys are jumping to the infinity thing right now, and I don't want you to do that. I want you to basically ignore, for the moment, we won't ignore it the whole time, I want you to ignore that. I don't want to have an infinite number of rectangles. I want to have specifically n of them. I want a variable n of them. So if I wanted to do, so instead of doing n approaching infinity, if I wanted to do like 30 rectangles, I could just plug 30 in for n, right? If I wanted to do 100, I could plug 100 in for n. So forget the infinity part for a second. If I've got that full interval and I want to fill it with n rectangles, how wide would each of them be? Does that make sense? The full interval width from 2 to 5 is 3. So think this over. Think of it like this. If the full interval width is 3 and I wanted to use 3 rectangles, how wide would each of them be? Aren't you doing 3 divided by 3 to get that? If I wanted to take my interval width of 3, which from 2 to 5, and I wanted to put 10 rectangles in there, how wide would each rectangle be? 3/10, right? You just take the full interval width divided by the number of rectangles. And if we're doing it evenly, then each of them would be that wide. Is this making sense? Okay, I know this is a little out of the norm, but I hope that it's making logical sense. If I make too big of a leap, please let me know. So I'm going to go back to what Matt said. He said, there we go. He said, and I think we all agreed, that the base length of each rectangle would have to be 3 over n. So the basic concept is full interval width, in this case 3, divided by n. That's going to be your base length. So I'm going to say limit as n goes to infinity, sigma from I equals 1 to n of 3 over n times h. So the easiest thing, write the limit sigma and perhaps b times h. Second easiest thing is to figure out the base length. The base length will always be full interval width divided by n. So for instance, this one goes from 2 to 5. If it went from like 2 to 10, then the base length would be 8 over n. If I'm just making stuff up right now, if my interval, say, went from like 2 to 25, then the base length would be 23 over n, right? Full interval width over n. Is this sinking in? For real? I'm asking a real question. I'm not looking to get patted on the back like, oh yes, when inside you're saying, oh no. Any questions? Can try to do more illustrations if you need to. Okay, so then the final thing, there's 2 final things. Final thing is the height. See if this makes sense to you. I hope this does. Doesn't the height of the rectangle completely depend on the y value of the curve? Doesn't the y value of the curve determine the height of the rectangle? So what I would say is this. I'm going to use some very specific language that I think helps. I hope it does. So I'm going to replace the h. I'll just erase the h here. And I'm going to say that the height of the rectangle is going to be input cubed. Input cubed. Now why can I say that? I can say that simply because the curve's y value determines the height of the rectangle. And isn't the curve's y value simply x cubed? Input cubed. Now the input's going to be the last piece of the puzzle, also the most difficult to see. Maybe, that's debatable. But input cubed, right? That's whatever the input is, no matter how simple or complicated it is, that will give me the height of the curve, therefore the height of the rectangle as well. Does that make sense? Fantastic. Okay, so here we go. Input. This is the last step, and this is, like I said, sometimes the most challenging. Here's how you figure out your input. You can't just say the input is like 2.2 or 3 or 4.1 or some other random number in the interval, because aren't we going to like move across? Like as we add more and more rectangles, we're going to progress from the left side at 2 all the way over and finish at 5, aren't we? So here's how you do the input. There we go. We're always going to start off by putting in this little input piece. We're going to put the lowest conceivable input first. So like, of all the inputs I could put in for this particular situation, what's the lowest number that could go in? 2, right? 2 is the very lowest because that's the left edge of the interval. I could not possibly plug in anything lower than 2. So I'm going to put a 2 right there. But I can't just say only 2 because if I just plugged in a 2 only, I'd get that one little itty bitty height on the left side. I'd be ignoring the whole right side, the whole rest of it. So I need to add to this, and here's where it gets a little tricky. I hope this makes sense. If it doesn't, you need to ask a question. I'd be happy to try to answer it for you. As I move across the shape here, and I'm going to try to make this picture work for me. So if I start over here at 2, I'm going to use yellow for this. I hope it shows up. I start over here at 2, and then I work my way across, plugging in various x values to go across the page and eventually get to 5. So every time, like I start at 2 and then I move over, and I get to whatever I get to, and then I move over again, and I move over again. I'm getting these new inputs each time. Every time I move over to the next input, how far am I moving? Can you describe it? Say again? Say it one more time.
You're moving 3 over n.
I'm moving 3 over n. Can anybody describe it a different way? Aren't I moving a base length over every time? As I move from one rectangle to the next, let's see here. Here is, I'll try to do a super blown up view here. Yes. So here's my rectangles. As I move from 2 over to here, don't I move over a base length each time? Hello? Don't I move over a base length each time? I know Ross is captivating, but I'll try to get your attention back. So what, maybe just sit at my desk, Ross. So what you want to do here is ultimately you want to get to where Matt got to, and he said every time you move over, you're going to move 3 over n over, because isn't the base length of a rectangle 3 over n? Okay, so I'm going to put plus 3 over n, but then if that's all I did, just maybe clear yourself a spot there. If that's all I did, then wouldn't I just be starting at 2 and adding 1 rectangle over? So I got to have some sort of a mechanism to allow me to keep moving over, and the key to that mechanism is in the sigma. The key to the mechanism is the sigma. The I goes from 1 to 2 to 3 to 4 to 5, up to n, doesn't it? So if I did this, if I wrote it as 3 over n times I, as I progresses from 1 to 2 to 3 to 4 to 5, I then get to move across the picture from the first to the second to the third to the fourth to the fifth rectangle, and that is complete. That would be the correct Riemann sum expression for the area under the curve for this particular one. Now what we could do, we could keep going with this, and depending on how things go tomorrow, possibly we might actually run one all the way through and use those little formulas that I said you didn't have to memorize. We might run one all the way through and actually get an area, but this would simply be the setup. From here it would be a decent hill of algebra to finish it. So I'm going to stop right there, and I'm going to get a question from Matt.
I'm just curious, you wanted the lowest possible height that you could fit, right?
Yep, for the 2?
Right.
Yep.
Because it starts at I equals 1, that means, doesn't mean you move over the first rectangle?
So yeah, I get it. Yeah, so there's, we can use the squeeze theorem actually to prove that whether you use a left sum or a right sum, we eventually get squeezed down to the actual number, because n is going towards infinity. So if you think this through, if n is going towards infinity, whether you used a right sum or a left sum, aren't we still talking about 2? So that's kind of the saving grace. I kind of like using this sort of notation because I feel like if we started at 0, it'd be like, why 0? Well, I thought we'd start with 1 rectangle. But because of the limit as n goes to infinity, we can actually go either way.
So you could do times I minus 1, and that wouldn't...
Yeah, there would be some variations on that. I think you'll find that the AP test will consistently use this kind of thing.
Okay.
I think just because there'd be a lot of folks that would be like, I minus 1, that's not what my book said. They'd get confused. But I think your point is well taken, definitely. Okay, do you see now why I don't have a lot of examples planned for today? Okay, so I want to see if you guys can fly a little bit on your own. And you might fall flat on your face. And I hope you don't, but if you do, we'll pick you back up and dust you off and give you another chance to fly, right? But you have all of this in front of you. Let me review the steps. Bless you. Always do the easy stuff first. So step 1, write down the limit sigma, right, of b times h. So that's a good start, right? Second thing is figure out your base. Now your base is always going to be interval width divided by n, always. So I'm telling you a couple of always things. It's a pretty bold statement, and so run with it, right? Once you figure out your base, figure out your height. The last piece of the height is always dealing with the input, which is that last little expression we did. Okay, so if you guys would, look at number 5. Depending on how much time we have, we might do another 1 or 2 examples. They're pretty easy to make up, so be happy to do that if we have some time. Colin.
So we're just writing the expression, not
Yep. Just write the expression only. I would say that...
Can't be too different.
So number 5, again, I think it's important for us to remember and understand the words that are telling us what we need to do. Notice it says, set up a Riemann sum expression to find the area bounded by ... So as soon as you see words like that, if I were you, I would write down limit sigma. So limit as n goes to infinity of sigma from I equals 1 to n. And then you could put base times height in there. Okay, so that's the easy step, right? They're all going to look like that. Now I got to figure out the base and the height. Noah, what did you have for a base?
I have 1 over n.
Would you mind explaining how you got that?
Most of it was just looking at the last problem where the distance was 1 from 2 to 1,
Mm-hmm.
or 1 to 2.
Yep. And so, yeah, full interval width is 1. Why dividing by n for the base length?
You have to go over n at each time.
Close. I would say that would help us with our input when we get to it. How many rectangles am I trying to squeeze into this pink area? Yeah, n, like some unspecified number, right? So if I take that full interval width of 1 and I try to put n things in it, they would all be 1 over n wide. Does that make sense? So I agree with you completely that the base length is 1 over n. So Noah got us off to a good start right there. Now we got to put in the height, right? So on the height is going to be determined, Hannah, by what? Say again? Yeah, close. I agree with your f of x concept, but it's not that we're going to be plugging in the base length into f of x. That's going to be part of it, isn't it? What tells the rectangle how high to be? The curve, right? The f of x, the curve. Yeah, I agree. So the curve is how tall? Oh, how tall is the curve?
4 minus x squared.
Doesn't it kind of depend on what x is? And specifically 4 minus x squared? Yeah, so the height of the curve is going to be 4 minus input squared. So we essentially have it right here. If we can just fill in the correct input, we've got it. Okay, so the input. Josiah, what do we always put in for the first element of the input?
I put 1
Why did you pick 1?
because that's where the curve, or that's where you're trying to find the area under the curve or stuff.
That's where it starts, right? That's the key. That's the lowest possible input, right? Okay, so 1, I agree. But of course, if we just start there at 1 and we stop there at 1, we didn't get the whole area. So we need to add to it. What do we need to add to it?
1 over n times
So why did you pick that to use?
because 1 over n is the base times I, which is the number of wherever you're trying to find.
And what's the I doing in this process?
Increasing.
Yeah, by integers, right? 1, 2, 3, 4, 5. Yeah. Yeah, I think that's it. That looks really good. You guys have any questions? Well, I must say I'm encouraged.